Welcome back. So today I'm going to spend a little bit more time talking about the Hadamard test. And further, I'm going to discuss some applications of it. In particular, I'm going to show how you can use the Hadamard test circuit also for eigenvalue estimation, as well as for to clarify how you can use this in order to be able to compute different types of probabilities. Then from there, we're going to go on and talk about the swap test, which you can use in order to be able to figure out what the overlap is between two different quantum states. So let me begin by sharing my screen. Okay, so screen is now shared. If we recall from our last lecture, the Hadamard test was a quantum circuit that looked as follows. It begins by applying a Hadamard transformation on one ancilla qubit and has a quantum state psi off to the side. Then it applies a controlled unitary gate where U is whatever unitary you feel like. And then at the end of all of this, you measure. So the probability of you getting 0 out of this is 1 plus the real part of psi U psi over 2. And of course, the probability of 1 is just 1 minus the probability of 0, which is equal to 1 minus the real part of the exact same quantity, divided by 2. All right, so we can use this in order to do a number of different things. First thing, of course, last time that we ended up seeing is we can use this in order to be able to measure the probability or measure the bottom qubit by measuring the top one. But let me show you another example. So normally when we measure a quantum state, what we do is we will measure in the computational basis in quantum computing, by which I mean that if we have a state psi, this will go to a state, like say we're measuring the entire quantum state. Then it'll go to a quantum state J with probability. Well, we can write the probability as psi, projector onto J, psi, which is equal to, of course, the absolute value of the inner product of psi and J squared. Awesome. So this gives us, again, the formula for figuring out the probability of measuring and getting a particular computational basis result out. But the computational basis is just one basis. So a question that naturally might come up is, well, how could we do the exact same type of measurement, but in a different basis? So let me show you. The key idea behind this is seen from a slight modification of the swap test circuit. So we can end up seeing, for the case where we're using it to measure psi in the computational basis, we took U equals Z. Now, again, we can end up writing Z as simply we can end up writing Z as simply projector onto 0 minus the projector onto 1. And as a result, we have that the identity plus poly Z is just over 2 is just equal to the projector onto 0. So we have for this particular case that, of course, the probability of 0 is just 1 plus the real part, but because this operation Z in this case is Hermitian, the expectation value has to be real because that's one of the properties. All Hermitian operators have real eigenvalues. And as a consequence of all Hermitian matrices having real eigenvalues, it's impossible to have psi U psi imaginary. And you can see this just by doing a eigen decomposition from it. And then you'll see that if the eigenvalues of U are real, because the inner products of the eigenvectors of psi on either side of the U will also give real numbers, the result has to be real. But in any case, we have that the probability then of 0 was actually just 0 psi absolute value squared. Okay, wonderful. So that's how we could do this. You might ask, well, what would happen if we changed U to X? Well, actually, it's very similar, right? Because as you recall, X and Z, they're related. In fact, there's a basis transformation that you can do to translate between Z and X. And it's the Hadamard transform that ends up mapping the poly Z operation to the poly X operation and vice versa. And in particular, we have that HZH is equal to X. Okay, so if that's the case, that we can transform between the two, then it stands to reason that a very similar type of transformation would happen. So now let's define the Hadamard gate acting on 0 to be equal to the plus state, because I don't want to write all the 1/√2s over and over again. And similarly, I'm going to have it acting on 1 equal what I'll call the minus state. And because the unitary transformations maintain inner products, i.e. it maps an orthogonal basis to an orthogonal basis, these two are also perpendicular to each other. Okay, so we have that this basis is true. So further, we can end up seeing the following, right? Well, what is X acting on plus? Well, X acting on plus is X acting on 1/√2, 0 plus 1, which is just 0 plus 1/√2. Similarly, it's easy to see that X acting on minus is equal to 0 minus 1/√2. And so we end up finding that X is equal to the following. We end up seeing from this that X is equal to plus, minus. Okay, and when you expand all of these out in terms of the matrix in terms of their definitions, we end up getting that the X operation is just, well, that, once we do it. But in this basis, we end up finding that it's of this form. Now, another alternative way that we can derive this is just by using the fact that Z is equal to 0, 0, minus 1, 1. And this implies that X is equal to HZH, which is then, by this definition, equal to Hadamard 0, 0, Hadamard minus Hadamard 1, Hadamard at the end. And then using the fact that that 1 Hadamard is equal to the conjugate transpose, or the Hermitian transpose of H1 over here, which is equal to, in our case, minus. We end up finding that this is just, of course, plus, plus, minus, minus, minus. Okay, cool. But we also have actually something even nicer. We have that in this basis, the identity operation is equal to, well, 0, 0, plus 1, 1. Okay, now when we Hadamard transform this, we end up finding that H identity H is equal to identity, which is equal to plus, plus, plus minus minus. Now, in general, actually, this exact same thing is true. Any unitary conjugation of the identity yields the identity. So we can, the identity will ends up taking exactly the same form in any basis, which is something that's really neat about the identity. So we have that this is true. So therefore, because the probability of 0 for these systems is equal to, well, 1 plus the real part, which of course is the entire vector for the entire expectation value for x, because x is Hermitian, divided by 2, is just going to be equal to psi identity plus x psi divided by 2, which of course is equal to psi plus minus plus plus minus. Wow, that sounded really weird to say. I hope it made some sense when I was trying to say it, but that is the algebraic expression for it. Now, when we go through the whole thing, we see that these two cancel, those two add, and we end up getting that this is the absolute value of psi given plus squared. So what have we done here? Well, this says that the Hadamard test can be used to measure in different bases. So in particular, just to clarify, right? Standard measurements we could do, in order to measure the probability that psi would be measured to be in the 0 or 1 state, right? But by using the Hadamard test, we can do exactly the same thing, but in an arbitrary basis, just by choosing an appropriately unitarily transformed operator. So if the basis transformation was carried out by an operation V, say, then we can if we apply the Hadamard test on the matrix V, Z, V dagger, then we'll end up getting exactly an analogous result, that this will be can be used in order to do a measurement of the quantum state in the basis where V maps between the computational basis to some other basis that we're interested in measuring the system in. So that is, in a nutshell, what the Hadamard transform is largely used for. It's used to give a nice way, given only the ability, like we have in quantum computing, to measure in one basis naturally, to generalize this to measure in an arbitrary basis. But I should mention there's other neat things that end up happening. Let's say that we end up having a state that has the following property. And this is something known as phase estimation. We'll return to this later, but estimation, yeah, some words. So phase estimation, the idea basically behind that is if we have a state that's promised to be of the form u psi is equal to e to the I theta psi, i.e. psi is an eigenvector of u. If we have that property, then we can actually end up using this type of circuit to estimate what the eigenvalue is. So let me show you how that ends up working. So we do exactly the same stuff that we did previously. We apply a Hadamard gate, then we apply U down at the bottom, and then we Hadamard, and of course, measure at the end. This will begin as 0, this will begin as psi, and then, well, of course, what ends up happening? Well, Here, we end up finding that the probability of 0 is equal to 1 plus the expectation value in the eigenstate, and I should say the real part of that, of u psi divided by 2, which in our case, the real part of this expectation value is actually just using the fact that e to the I theta is equal to cosine theta plus I sine theta. Then this is actually just 1 plus cosine of the eigenvalue divided by 2. So let's say that what we wanted to do is we wanted to be able to estimate this particular eigenvalue that we have coming out of it. Well, what we could do is we could just prepare an eigenvector, feed it into the system, and repeat this process in order to be able to come up with an estimate. When we find the estimate, p hat, we then would set this equal to 1 plus cosine theta divided by 2, and we end up finding that the eigenvalue is equal to the arc cosine of twice the probability estimate that we end up getting minus 1. So this gives us a way of estimating the eigenvalues. But I should mention there's actually something kind of neat that ends up happening to the particular to quantum states that end up coming in. It turns out that if we have a quantum superposition of different eigenstates, then applying this will actually end up leading to the state collapsing ultimately, once you apply this method iteratively enough times, to one of the individual eigenvectors. I won't go into that in great detail yet, but I wanted to mention this in order to kind of like prime the pump for when I talk about phase estimation methods in greater detail later on. The Hadamard test is just a particular example of one of the simplest ways that you can carry out phase estimation. And also I should mention the least efficient. But so that is how phase estimation in a nutshell ends up working. Now, let's move our attention on to a related problem. Let's say that what I've got is, here's my problem. Let's say you've got two different types of quantum states that are given to you. You've got a state psi and a state phi. And the problem is you'd like to determine whether or not these two states are the same or different. So are they the same or different is the question. So the way that you could determine whether they're the same or different, the easiest way is by using this quantum circuit that we call the swap test. And the swap test is actually really spiritually related to the Hadamard test. The idea is it begins with, just as before, you prepare an ancilla state in 0 and have a state psi and phi over here. You perform a Hadamard transform, and then what you do is you do a controlled swap operation on these two states. Then you apply Hadamard transform to kick it back into its original form, and then you run forward, and you guessed it, you measure this bit at the top. So the basic idea that ends up happening, again, you can end up thinking of the Hadamard gate as like splitting your computation, which initially begins in the state psi phi, into two different possibilities. One where it remains as 0 psi phi, and the top one ends up being 1 psi. Well, okay, I won't use the comma notation, but then, of course, what we do is we have the swap, and the swap gate, what it does is it ends up just swapping the two inputs, and we'll have phi psi kicking out of it. Then we apply the Hadamard. These two possibilities get recombined, and interference ends up happening. And that interference actually causes this value up here to be 1/2 the absolute value of the inner product between psi and phi squared divided by 2. Okay, so let's go through the algebra to see why that's true. And again, the key definition of swap can be given on its action onto tensor product states. Swap phi psi phi is just phi psi, meaning that basically these two end up getting exchanged and those two get exchanged in the ordering of the tensor product. So basically, just to see this visually in the quantum circuit, if you had a tensor product of two states input over here, you would have psi and phi. And just remember, if you don't have a tensor product of states, what you do is you can just use the linearity property of swap to end up doing something like swap 1/√2 psi phi plus phi psi is equal to 1/√2 swap of the first term psi phi plus swap of the second term phi psi, which in this case is exactly the state we started with, 1/√2 psi phi plus phi psi. Okay, cool. So that's what ends up happening here, but let's go through the analysis. So the very first step is that we apply the Hadamard gate. We have 0 psi phi, and after the Hadamard gate, this goes to 1/√2 0 psi phi plus 1 psi phi. Now, next step is we apply the controlled swap operation. And again, the controlled swap will only swap on the top branch, i.e. the branch where we have 1 in the first qubit. And so this won't do anything to the first term, but it'll end up swapping the tensor factors in the second term into phi psi. Okay, now the last step is we apply a Hadamard transform again to this, yielding 1/2 of 0 psi phi plus phi psi minus 1 psi phi, or sorry, plus minus phi psi. And there you have it. And the minus sign again, this just comes, just like the Hadamard test, it comes from the minus element in the bottom right corner of the Hadamard transform matrix. So this is the resulting state that we've got. Now, there's something actually kind of neat that you can see. You can see that what this is doing is this is mapping the state to a linear combination of a symmetric combination of phi and psi, and an anti-symmetric combination of phi and psi. For example, if I swapped these two, I would get a -1 sign. If I swapped those two, I would get a +1 sign. So this is actually doing something kind of cute. What it's doing is it's transformed the state to now be an entangled mixture of a symmetric superposition of the two states and an anti-symmetric superposition of the two states. And in fact, that's another way that you can look at it, is that the swap test actually implements a projector onto the symmetric or anti-symmetric subspace. But I'll talk about that more later when I go into detail in linear combinations of unitaries. So this is what we end up getting. Now I'm going to call this state over here chi. Okay. Now and I'll copy and paste it. Oh, let's ignore this nonsense. There we go. Copy and paste this, paste it here, and there you go. And now, once we have this, the question is, well, what's the probability of measuring 0 on the first qubit? Probability of 0 is just, as we've established before, we want the first qubit to be 0. So we'll put a projector onto 0 there for the qubit that we demand to be 0. Next, we don't care what the state the first tensor factor is in, and we also don't care the second tensor factor when we're counting the probability. So this ends up being our expression. Now, this expectation value is only going to take terms from this part of the branch. So I won't bother writing down these because the projector onto 0 has no inner product with 1. So what we end up with is that this guy is just equal to 1/4 psi phi plus phi psi times psi phi plus phi psi. Okay, so we'll just expand this out and note that, like, for the example, for the first term, because the inner products of tensor factors end up distributing, we have the inner product between these two is the product of the inner products of the tensor factors. And we end up getting that this is just 1/4 of 1 for those inner products, plus, well, another 1 from these two. But the cross terms are a little bit different. What we end up getting for those is we end up getting that that is psi phi phi psi times 2. Okay, so what's psi phi times times phi psi? So if we take a look at that, well, psi phi is equal to, clearly, phi psi dagger. And because this is a scalar, this is equal to it's equal to psi phi complex conjugate. So we can end up, of course, writing this as 1/2, 1 plus psi phi times psi phi complex conjugate, which is actually the very definition of the claim I had to begin with. This is just defined to be equal to 1 plus the absolute value of psi phi squared. There you have it. This is how you can use the Hadamard test in order to be able to measure the probability of two states being seen to be the same. Now, it's actually very interesting test because, again, if we take a look at this, drawing it all out, right, we've got swap gate down here, and this is psi, and that's phi, and feeding in Hadamard over here, and measure. Okay, so this is what we have for the particular test. Now, the thing that's interesting about it, again, is that the probability of getting 0 is equal to 1 plus psi phi absolute value squared over 2. Let's consider two extreme limits. Let's say that the two states are exactly the same. If they're exactly the same, then their inner product between the two is going to be equal to 1. So in that case, if the two are, the inner products are 1, then the probability of 0 is equal to 1 plus 1 over 2 equals 1. All right, not so surprising. You have two states that are the same with 100% probability. When you pass those states through the system, you will get 1. Now, let's imagine the opposite situation. Let's imagine that the inner product is 0. Then, if psi phi is equal to 0, then the probability of 0 equals 1 plus 0 over 2 equals 1/2. So this is one-sided. So let's say that, for example, you perform the experiment and you measure 1. This implies with 100% certainty psi is not equal to phi. So a single application of this circuit can actually determine if two quantum states are not the same, which is pretty cool. However, if we measure 0, then it basically says that, I don't know, you have to use statistical inference in order to be able to figure out what, whether or not you believe, or with high probability, the two states are the same, or if there's some decent probability that they're different, and you just got unlucky. All right, and so here's a relatively straightforward claim. There exists an algorithm. Okay, so actually, let me just go back to the game that we were talking about before. So jumping back before I state the claim, there's this problem, right, where we're fed in a bunch of psis and phis, right? And we want to be able to determine if they're the same or they're different. And so my claim is that there exists an algorithm that takes for any, or sorry, there's just an algorithm that takes a state of the form psi tensor n and phi tensor n, or actually, just to be a little bit clearer, let's say tensor product between those. So we have n copies of the state psi and n copies of the state phi. And then if n is greater than n is greater than log of, how does it go? I think it's 1 over delta divided by log of 2 over 1 minus p naught ceiling, where you promise that the absolute value of psi given phi squared is greater than or equal to p naught, then what you end up having is that you can determine whether psi equals phi with probability of failure less than or equal to delta using this number of copies of the states. And the proof of this is actually just straightforward, okay? So the proof is the probability of the Hadamard test, or sorry, the swap test successfully telling you that the two states are different is the probability of 1, which is 1 minus the probability of 0, which is equal to 1 minus the absolute value of psi phi squared over 2, okay? Which, again, if the probability, if the inner product between these two is less than or equal to p naught, then this quantity, again, is going to be greater than or equal to 1 minus p naught divided by 2. Now, if we repeat this process, if the process is repeated n times and no 1 is observed, then you would potentially erroneously conclude that the two states are the same. And the probability of not having seen a distinguishing measurement, given that they are potentially far apart as specified by this delta parameter is given by, or this P naught parameter is given by, well, just the probability of failure repeated n times. So it's just that to the nth power. Now we want this to be set equal to delta, which ends up implying that n log 1 minus p0 over 2 equals log delta implies that n, and this we can have this process hold if n again is taken to be greater than or equal to the ceiling of log 1 over delta divided by log 2 over 1 minus p naught. So you see that with a complexity that scales logarithmically, with the amount of uncertainty that we need, we can actually repeat the swap test over and over and over again and say with confidence that actually the quantum state at the end will be distinguished if we have this bound on the probability of or the overlap on the states. So subject to that constraint, then we can end up saying that repeating this n times, where n is given by that value, and with given probability of failure delta, we are actually going to succeed within that probability of failure. So that's basically the idea of how we can use this protocol for state distinguishing. So, well, thank you very much. I hope you liked it. Next time we'll jump in and talk about teleportation. See you all then.